I'm always relieved when the first week is over. It's always kind of a good feeling. And of course, we have to get through the first full week, right? But do y'all have any questions for me before we roll into the rest of these lecture slides? So don't forget, homework 1 is due Friday by 59 p.m. in Gradescope. So the Gradescope file has been released, so it's available now for submissions. And disregard the points allocation. I don't know if you can see that when you upload your tag things, but disregard that. We don't put that in until later. So yeah, it's just whatever the default habit has. All right. So last time we left off talking about, we had just finished talking about different types of structural connections, right? So we looked at different configurations for roller supports, pin supports, and moment connections for steel, and we talked about reinforced concrete, and we talked about how wood connections are typically assumed to have pin behavior. And that's because it's very difficult to achieve full moment transfer with wood members. So now what we're gonna do is I'm gonna talk a little bit about an internal hinge or a pin, which may be somewhat of a new concept for you guys. You may or may not have seen this in your statics and mechanics classes. I'm not counting on it though, so I'm treating this as though this is kind of the first exposure to an internal hinge. And we'll talk about that behavior, and then we'll also look at it later today, technically in the lecture 3 slides. Good morning. And we'll look at that and consider how we analyze a structure that has one of these internal hinges in it. So essentially the most important thing to remember with internal hinges or pin connections, it's essentially just a pin connection between two members, right? And there's no external support associated with that connection. So this connection cannot transfer moment, right? So moment is equal to 0 at that hinge location, and that's the internal moment, right? It doesn't mean that you can't apply moments to the system. It just means that if you draw the moment diagram, it's always going to be 0 at the location where that internal hinge is present. So it can transfer axial shear forces, right, not moment. We idealize it by just drawing an open circle. And in this class, I'll always point out when it's an internal hinge for you, just to avoid confusion, because we'll also be looking at nodes later on and when we do finite element analysis. So that's going to be a potential point of confusion. So hinges will always be called out as hinges in this class. And it's usually pretty obvious in the textbook as well. When the textbook has problems with an internal hinge, they make it pretty obvious. A more realistic representation might look something like this, right? So it's a plate with some bolts that attaches to two ends of two elements, right? Now, if a transverse load is applied, right, because there's no external support associated with that hinge location itself is free to displace, right? So it doesn't prevent motion, but it just keeps those two pieces attached in terms of vertical and horizontal directions. All right, so we'll look at a few actual internal hinges or pins. It was a little bit tricky actually to find images of these, and this one is even a little bit more unusual because it is technically, I would call this an internal roller, because you can see the long slotted holes peeking out behind this tab. So that indicates that it's free to kind of shift back and forth along the axial direction. And this, I imagine, is some type of temporary configuration. Like this would not, I can't imagine that this would actually be part of a complete structural system. So it's probably some kind of construction support or something like that. So that's one example there. here's an example of an internal connection between two members that is not a hinge. And the difference, right, you can see is substantial. You still have the two, the flanges, or excuse me, the webs, right, of these members are still attached with a plate with some bolts. But then look at all the bolts that are attaching these thick plates to the top and bottom flanges of those members, right? That is what enables Moment to pass through that connection and be transferred from one of these members to the other one. So this would be considered a full beam splice, right? So when we splice an element, we assume, or the goal is to make sure that all of its capacity is transferred over to the other side, right? All right, so now that we've talked about all the different types of connections and joints and shown examples, you know, and we've talked about the different types of elements, right? We defined that last week. A structural system is an assembly. What did I call that? Structural assembly? Yeah, structural assemblies, all right, of course, are assemblies of different elements using these connections that we described. So a frame is an assembly of beams, columns, and flat plates. Two force members assembled together form trusses, all right? Remember what a two-force member was defined as? Do you have a... Yeah.
Oh, a member with equal and opposite forces.
Right, yeah, so the internal forces are all aligned. Yeah, so it's arranged that internal forces are all aligned. And when you do those cuts and you expose those internal forces, they will be equal and opposite. Yeah. All right, so here we have a bridge, right? So this is an assembly of what elements would you identify in this bridge? Yep, cable. What else? Ties. Ties and cables are synonymous.
Girders.
Beams. Yep. Yeah, you need some long beams to span between those columns. Yeah. And then technically we could also throw in there some flat plates for the road surface, right? So ties and beams and columns are basically the backbone or the skeleton of this cable-stayed bridge, right? And so that essentially is a structural system, all right? Basic categories of structural systems, we've got buildings, bridges, and those are going to be the main applications that we're going to focus on in this class. But there's also dams and tunnels that are kind of in their own category of structural systems, right? So that ends the lecture 2 slides. Any questions so far? All right. All right, so now we're going to roll into the lecture 3 slides, all right, which continue this concept. So we've got, now that we've introduced structural systems, all right, we're going to talk about some basic analysis concepts, and then, so this will be a little bit of review of statics and stuff that you've seen before, but also defining maybe some new terms. And then we'll dive into specific types of structural systems that are used in buildings, right? So, and this lecture I expect to spill into Wednesday for sure. And then on Wednesday, we'll probably start talking about gravity load path. So that's the lecture 4 slides that are posted. And then by Friday, by Friday we should be into the skeleton notes. All right, so that's the lecture 5 set that's posted on D2L. All right, so basic analysis concepts that you're going to be focusing on a lot in this class are determinacy, stability, and static equilibrium. Static equilibrium, for sure, you're already familiar with, right? That was introduced in statics, and you revisited it in mechanics. Determinacy and stability, we're going to talk more about that in this class. So we'll go through and define, or first we'll go through and recap static equilibrium, all right? And then we'll go back and look at determinacy and stability. This is kind of a goofy picture. Has anyone been to Chicago and up to the Sears Tower, or now it's called the Willis Tower? They have a sky deck that is a glass enclosure, not very big, but a few people can stand in there at the same time. And all 5 sides of the enclosure are glass, and this is up towards the top of the building. So you step out there, you can look down and see the cars between your feet and stuff. So it's kind of a weird experience, but that's definitely, I put it out there just to show the level of trust that we put in our structures. So we want to make sure that they meet all these criteria. For static equilibrium, all right, as you know, you have 3 sets of equations that you can use to evaluate equilibrium for 2-dimensional structures. So this one on the left is the most commonly used set, right? But you can also use this set to establish equilibrium, or this set, right? So on the right side, you've got just summing moments, but you're summing moments about 3 different points. The criteria for this one is that these 3 points cannot be on the same line, all right? So if you have any 3 points that you want to sum moments about, as long as they're not on the same line, you can establish that equilibrium is met, as long as those equations sum to 0. And of course, you're familiar with free body diagrams. We use those to identify applied forces and find reactions. So it's a basic tool that we use. You always want to draw your free body diagrams when you're evaluating static equilibrium. And now that we are dealing with internal hinges, all right, there's a strategy that we need to consider. We may not always need to use this strategy, but as you know, right, you've done this before, you can break the structure into multiple free bodies. And we'll look at this in an example in a little bit. When you do break the structure, you have to think about what internal forces you're exposing, right? And you have to include those as unknowns in your free body diagram. So having that internal hinge gives us an advantage when we have to do this, and we'll see that later. Again, though, that's not always necessary to break it apart. And then I want to point out here that these 2 equations are not the same thing, right? So over here, this is saying summing the moments about A is equal to 0, right? That's one of your equilibrium equations. That's not the same thing as saying the moment at A is equal to 0. So I just want to put that out there because there's always some confusion tied to that, and I just want to make sure everybody's on the same page here. All right, so now determinacy and indeterminacy. Are you all familiar with these concepts yet, or this is new? Yeah, okay, that's kind of what I expect. This is a new concept. All right, so not all structures are determinate or indeterminate, but the ones that we want to work with are, all right? So basically, if we define the number of external reaction components, right, count those, that's NR, and then NE would be the number of equations. So for a 2-dimensional structure, the number of equations is always going to be 3 from your equilibrium equations, right? So you've got 3 equilibrium equations for every free body diagram. Plus, again, for every free body diagram that you have, how many internal hinges are there? So the number of internal hinges provides us with an extra equation. We call that the equation of condition, right? And that condition is that moment is equal to 0. So, let's see, I didn't spell that out on there. All right, well, we'll see that later. Now, if the number of reactions is equal to the number of equations, then the structure is determinate, meaning we can solve it with just those equations that we have, right? The 3 equilibrium equations plus however many hinges there are. If we have more reactions than equations, then it's structurally indeterminate, statically indeterminate. That means we can't solve it using only statics, right? We need some help, we need some more advanced methods to solve it, and you'll learn some of those tools in this class. But it's important to identify first if you have a determinate or an indeterminate structure. It's also important to remember that if your structure is determinate or indeterminate, that does not necessarily mean that it's stable, right? So stability is a separate thing that we have to evaluate. These two examples, right, of a determinate and an indeterminate beam, these two are both stable, right? But in general, these equations being satisfied does not mean stability is satisfied. So just remember that. You have to check that separately. However, if your structure is neither determinate nor indeterminate, right? In other words, if you have fewer reactions than equations, then you can conclude that your structure is definitely unstable, right? And you don't have to analyze it because we don't want unstable structures in this class. We'll talk about that more in a second, but here are a few more examples of different types of structure and evaluating their determinacy. Or in this case, right, this one's unstable because you have two rollers. So that's only two reactions and you have three equations, so it's unstable. Intuitively, you can tell that it's unstable too, right? Because if it's got just two rollers, then there's nothing preventing motion in the horizontal direction. So the first four here are beams. This fifth one is technically a truss, right? So if you have a pin, an internal pin, and then a pin support, then as long as those three are not aligned, so if you can't draw a straight line that goes through all three of those pins, then it should be a stable truss, right? We'll look at the other condition later and show how that's an unstable setup. If this pin was down here and aligned with these two, that would be unstable. And then here you have an indeterminate frame, and then again that unstable beam. So the other thing that's noted on here is the degree of indeterminacy, right? So you'll see that for these indeterminate structures, it says second degree, first degree, fourth degree. The way that you determine that is by taking the difference between the number of reactions and the number of equations. That gives you the degree. And so what the degree tells you is essentially how many, you can think of it as how many assumptions do you need to make to render this determinate. So that's something that we'll look at later on in this class in the context of approximate analysis. Or in finite element analysis, all right, it actually, you'll see that the more indeterminate a system is, the easier it is to solve using matrix solutions. So we'll come to that later in the class. All right, so now back to stability. As I alluded to earlier, all right, an unstable structure is something that can move without deformation, right? So that's the second bullet point down here. If it's moving without deformation, that means it's undergoing rigid body translation or rotation. So if you have rigid body movement, then that's not causing internal stresses or forces, and that's unstable. So all the structures, or all the configurations, I should say, that you dealt with in eGen 202 dynamics, those would all be considered unstable in this class. So we don't want rigid body motion under any load configuration. And if we don't have rigid body motion under any load configuration, then we can say that our structure is stable. And another way to put that is that it's in static equilibrium. Now, there are some conditions that you want to keep an eye out for, right, when you're evaluating stability. So these are called geometric instabilities. And these are examples of where these structures would come out to be determinate, all right? So the number of reactions is equal to the number of equations in both cases, but they're both unstable. So here with this frame, you have a roller support down here. The line of the reaction force is going to be perpendicular to the surface of that roller, right? So here's the line of reaction for that one reaction force in a roller. The pin support, all right, we can break that down into an X and a Y. And since all three pass through the same point, that means there's no resistance of rotation. There's no resistance to rotation about this point, right? So a force can cause this to rotate about that pin. Now it's common to think, well, this line is on a slope. You can break this reaction into a vertical and a horizontal, and then you have 4 reaction forces. Well, you can break it into a vertical and horizontal, but the difference is you know for a fact the direction of the resultant of that reaction force, right? Here, you don't know for a fact what the resultant direction is for the vertical and horizontal, right? So that's why we can say, yeah, this is unstable. So if all the reaction lines cross at a point, then it's stable. And again, if you have a pin support, internal hinge, and then a pin support all aligned so that you can pass a line straight through them, then that's an unstable configuration. And we'll look at that more closely later. All right, so any questions so far? Okay. All right, so now we'll look at an example of evaluating the reactions of a beam that has an internal hinge. All right, so this beam has a pin at A, a roller at B, an internal hinge at C, and then a roller at D. All right, the sketch is a little bit unclear, but this is a roller. It's got the 2 circles below a triangle. And then our strategy here is going to be to break this structure apart, because if we don't, we have 4 unknowns, right? We can't just use our 3 equilibrium equations on this beam. But we have that internal hinge, right? Now that gives us an extra equation, that equation of condition. The condition being moment is equal to 0. So knowing that moment is equal to 0, if we break, right, do a traditional cut through a section, we would expose internal shear, internal axial, and internal moment. But if we break it here, we know that internal moment is 0. So that gives us an edge, all right? So we only now have a segment that has 3 unknowns. The reaction at D, and then the internal shear and axial force at C. All right, so if we consider that right side of the beam and isolate that as our free body diagram, summing moments about the hinge at C, we can solve directly for the reaction at D, right? So we would get 4,000 pounds acting upward at D. From there, we have 2 options. We can either stick with this free body diagram, sum forces in Y to find FCY, and then transfer that force to the other side. If we transfer the force, we would take whatever value we found here and equal and opposite on the other side, right? Apply it that way. Then, knowing that force, we could go to the right side free body diagram, and we have 3 unknowns, and we can apply our sum of forces in X, sum of forces in Y, and sum of moments to get those 3 unknowns. But that's a little bit of extra work, right? A more efficient way to go about solving for those reactions would be to just, after finding the reaction at D, go back to the whole beam, right? So piece it back together, and now we only have 3 unknowns. We can apply our 3 equilibrium equations and solve for the remaining reaction forces, okay? So if you're not interested, if you don't need to find the internal forces at the hinge, then there's no reason to do that. You can skip that and go straight to just finding all the reaction forces. And then another thing, another thing I'd like to point out before I forget is that whenever you draw final free body diagrams, this is a good thing to always do in your work, make sure that you represent the applied loads as they are truly distributed, all right? So we simplified this. This was how it was presented in the original problem, right? It was a distributed load of 800 pounds per feet. We simplified it to a point load for the purpose of solving for equations for our reactions, right? But you always want to return it to its actual distribution. Do you know why? Why do I care?
Wouldn't it change how it like causes a moment from like on this side?
Absolutely, yeah. So it's going to affect your shared moment diagrams. If you forget and you just stick with the point load that you used to find the reactions, and it's fine to do that for finding reactions, but that's going to mess up your shared moment diagrams if you don't return it to a distributed load. So yeah, that's absolutely correct. All right, Nick, do you have a question?
Do you just flop the FCY like force on the left side of it because it's a hinge? Like,
Yeah, well,
the one was up and then
so-
the other side you switch it to have it down.
Yeah, so any time you cut through a section, it doesn't matter if it's a hinge or not. If you find the internal forces that are acting at that cut, then if you go to the other side of the cut, you would apply those forces in equal magnitude in opposite direction. Yeah. So this was assumed upward, right? And I would expect it to be turn out to be an upward force, but if, for example, you found this to be a negative value when you solve for it, then that would just mean that it's a downward acting force and this would be an upward acting force. Yeah, any other questions? Okay. Let's see. I already talked about that. All right, yeah, okay, so this was just a recap, right? So again, remember this is what it might look like in real life. And then going back to, right, our internal hinge or pin. Again, moment is equal to 0 at the hinge. And then what we're gonna do now is take a look at a configuration in the context of a frame. So here, these columns are supported by a fixed support at the base, so the columns themselves are stable. And then they have a pin connection to the beam. But because the beam has an internal hinge, it's not a stable beam, right? So we're going to prove that now. We're going to isolate this beam, all right, pull it out of the frame. And then this is an example of, remember last time I said that in talking about the difference between supports and connections, there's a caveat, and sometimes we treat connections as supports for the purpose of analyzing a component if we pull it out of a structure. So this is an example of that, right? So we had pin connections to the columns, but since we know those columns are stable, we can go ahead and just treat those as pin supports if we're just considering the beam. So there's our free body diagram with the internal hinge shown. So if we apply equilibrium to the entire beam, just to write the equations out, right, this is what we would have, and we would be able to conclude, right, we wouldn't be able to solve for anything just yet, but we would be able to conclude that if some moments, right, we know that the reaction force at the left end has to be some positive value, right, greater than 0, but it's not going to be as large in magnitude as the applied load P, right? And same with R2, right? It's going to be some positive reaction greater than 0, but not as large as the magnitude P. They're going to share the load. We can neglect the horizontal reaction forces because we're only interested in the vertical. And then if we break that structure at the hinge, all right, we know that the moment is equal to 0 at the hinge. If we sum moments about the hinge, we have no applied force on this side, we would conclude that the reaction force, R1, is equal to 0, right? Because this moment is 0, we sum moments about the hinge, this has to be 0. But that's incompatible with what we found from the full beam equilibrium, right? We found that reaction R1 has to be greater than 0. So because that's incompatible conclusion, then it follows that this beam is unstable. Questions? Okay. All right, so now if this beam had a roller support on the right end, of course, it would be even more unstable, right, than if it just had a pin support on the right end. But if we put a roller on the right end and a fixed support or a moment connection at the left end, then that would be a stable configuration, even with that internal hinge. All right, so this is what an idealized sketch might look like, right? Fixed support, hinge, roller support. And this is a common configuration that you'll probably see in this class. Okay. Questions? Okay. So a lot of times in the books, the internal hinges might be idealized a little more obviously than just a line with an open circle. So if you see the tapering at the beam ends and the overlap like that, that indicates an internal hinge. All right, so now we're on to structural systems. As we talked about earlier, right, combining all these different components into a system is what we go for. Now, I'm going to talk a moment about trusses or truss systems, right? Because we can see truss systems in buildings. For example, here's the Bank of China. This is in Hong Kong. And this is what we call a space truss system for a building. So it basically behaves like a truss, but it's vertically aligned instead of horizontally aligned. And so the definition of a truss is shown up here, right? 2 or more axial force members that are pin connected at their joints. And so if we say something is a truss system, that may be referring to a structure that relies heavily on trusses or on truss behavior. So we'll talk more about that later. There are a lot of other different types of systems, right? So there are many, many different buildings, of course. They're all unique. Not just tall ones either. You've got the really expansive ones that have a huge footprint. And then you have a lot of the, smaller ones and older ones. So all kinds of different systems. But all of them need to be able to resist gravity loads and lateral loads. So what we do is we separate our analyses into looking at just the gravity loads and the system that's going to support those loads, and then just looking at the lateral loads and the system that's going to support the lateral loads. And many times these gravity and lateral systems are integrated. Sometimes the members play a role in both systems, but we could treat them separately, analyze them separately, and that's how I'm going to set up our class as well. So first we'll talk about lateral systems, but before we get into that, I'd like to just give you a brief overview of the most common types of structural loads. And I've divided them into gravity and lateral, as you can see. So the ones in red, right, dead loads for gravity and soil pressure for lateral, these both have very little change over time, right? So we consider them to be pre-stationary loads. The others, live loads, snow loads, and rain loads are all gravity, and then lateral is seismic and wind. Wind can be vertical as well, but these loads have a lot of different changes over time. They can change in magnitude, they can change in location of where they're applied, and they can also change direction. All right, so here is an example of gravity system and load path. And again, this is just one example, but essentially, right, you've got vertical loads that are applied to a floor surface. So that's one level of your structural system. The floor surface transfers those loads to beams, beams transfer to columns, columns transfer to the foundation. We'll come back to that later this week. An example of a lateral load path, right? You've got, for example, a wind load that applies a pressure to the wall surface. That wall surface transfers loads to diaphragms. So remember, we defined diaphragms as typically basically a floor, right? So the floor acts as a diaphragm to transfer those forces to the lateral system, and then the lateral system transfers those forces to the foundation. Now, of course, you do need a lateral system in both orthogonal directions of the structure. So we're going to talk now about lateral force resisting systems. If you think about just stacked beams and columns, right? Every child does this with blocks. You know, you can stack things and it can be stable conditionally, right? But as soon as a lateral force is applied to that, it's just going to fall over and topple. So how can we stabilize it to resist lateral forces? Well, maybe we start by attaching them together, right? So if all the connections are pinned, let's say, that's a step, but it's still unstable, right? Because a lateral force will just cause it to flop right over. They'll be held together, but they're not going to be able to resist that force. So now this is going to lead us into 3 types of lateral force resisting systems, right? So the first one is a braced frame. So if we start with that, just assembly pinned together, one thing we could do to make it stable is just to add a diagonal member, and then that will keep it from tipping over or flopping over under lateral load. So the characteristics of a braced frame are listed here. You've got pinned joints, pinned supports typically, and diagonal member or multiple diagonal members. So if you just have one diagonal member, we call that a brace a lot, then that diagonal has to be able to resist both tension and compression. Because if you reverse the direction of the force, it's going to change whether it's in tension or compression, right? So if I push on the frame this way, is this diagonal going to be tension or compression? Tension, right. And if you push on it the other way, it's going to be in compression. So that configuration is determinate, all right? If you have 2 diagonal braces, and if both of those members are capable of resisting tension and compression, then it's an indeterminate configuration, all right? Or maybe those diagonal members, if you have 2 of them, they could be ties, and then they're only able to resist tension, right? So in that situation, this is a determinate configuration, because if the load is in this direction, you know that this member is going to be engaged in tension, and this member is doing nothing. It's just going to be in slack, right? So we call that a zero force member. And then the roles would be reversed if the direction of the load is reversed. So here are a few examples showing that condition, right? If you've got tension-only bracing. And here are some examples where you have bracing that can resist both tension and compression. Here are a few buildings that have this system, right? So anyone recognize this one here? Maybe no? So this is in Chicago. It's the second or third tallest in Chicago, the John Hancock Center. And then I'm not sure what that guy is over there, but braced frames. Here are a few specific types of braced frames for your reference, right? You don't need to know those for this class, like those definitions. I'm just showing them to be aware that there are different specific types. All right, so now that covers the introduction to braced frames. Now we're on to the second type of lateral force resisting system, which is the shear wall. A shear wall would fill in a frame with a solid panel of some material that is able to resist shear. Common is reinforced concrete or reinforced masonry. You also see wood and steel used for these panels. Gypsum board is also often used for lower rise construction. So here are a few examples of different materials, right? You've got concrete, wood, masonry, and steel. Shear walls all in this picture. And these are also commonly used in high-rise applications. So, of course, the braced frame can get us to some great heights, but shear walls are also useful for that as well. But when we use shear walls in tall buildings, we often need to add an outrigger to help with that action. So I'll explain why. All right, so because we want the shear walls to be as solid as possible, right? We want to reduce or eliminate the number of openings to maximize the transfer of shear forces there. For tall buildings, we typically will concentrate those shear walls towards the center of the building so that they enclose stairwells and bathrooms and elevators, right? Things that people don't really care if there's windows or not, rather than being on the outside of the building, because then it's a battle of, my views are gone because these shear walls are blocking it. So we try to consolidate all of that towards the center of the building, but that also means that for a tall structure, that shear wall core becomes very slender, and then it becomes easier to kind of bend and flex and topple over. So that's when we introduce the concept of outriggers. So these are typically trusses that extend out from the shear wall and then grab onto the perimeter columns of the building to engage those columns in helping to resist overturning. Right? So it's a similar concept of why a skier uses poles for stability. Right? And also, side note, here's an example of a spring foundation being used in this model, right? Or spring supports. So again, we're not going to do spring supports in this class, but now you've seen it in an application. All right, so I'm going to show you an example of a couple high-rise buildings that use, I think one that uses an outrigger and one that uses a different way to engage the perimeter. But first, I want to introduce this concept. So this is a relatively new type of structural system. This is called composite steel plate shear wall. And so what this does is instead of using your traditional reinforced concrete shear wall, where you have rebar cages and then formwork, and then you pour the concrete in there, wait for it to cure, remove the formwork, move on to the next. Here you have two steel plates with studs arranged as shown. Concrete is poured inside, and that is your structural element, right? So the beauty of this is that those steel plates are part of the permanent structure, and they also serve as the formwork. So it really saves it's a lot more efficient materially for the construction, and also big time with regards to labor and time, because you don't have to wait for that wall to cure before removing that formwork and using it for the next level. So using this system, I think the first use of it was for this Rainier Square Tower, which is downtown Seattle, and it's the second tallest building now in Seattle. They used that system, and it saved them about 7 months of construction time, just using that system compared to the traditional reinforced concrete construction. So you can see in this rendering, right, the orange represents those shear walls, and then the red are the outriggers. So up here, they didn't have to do it until way up here on this building, but they've got that outrigger that extends out to the perimeter and engages those columns to help resist overturning. And they didn't need it in both directions, notice that, right? So they only needed it in this direction, but in this direction, right, they didn't really need it because the shear walls extend as far as the outriggers do. So in this direction, because it had more width at the base, it wasn't as necessary to get more assistance in resisting overturning. Another way to assist tall buildings in utilizing their shear walls to resist overturning and lateral forces is to implement what's called a belt wall system. So this is essentially taking a couple walls, or I should say a couple stories maybe, it depends on the building, but one or more stories in a row staggered over the structure, where those walls on the perimeter are solid, and then through floor slab, right, they transfer the lateral load from the core wall to the belt wall and then back to help engage that perimeter in resisting overturning. So that's just another way to do it. One famous application of this is the Burj Khalifa, which is still the world's tallest structure. So you can see these levels that look more gold, they're a different color. Those are the belt wall levels, and it's 2 or 3 stories in a row at each point. That's where they house the mechanical facilities for that building, so nobody cares about losing windows. But here's a look at the floor plan, and we've got the core, right, concrete shear walls, and then each wing has its own array of shear walls as well that extend. Some of them have these, wings that extend out to the perimeter, but the belt wall goes all the way around the perimeter. Let's see where we are in time. All right, 5 minutes left. It is toasty in here. They must have turned the heat on in the building or something. We had the opposite problem last year in Roberts 101. It was freezing in there for into October, and then finally they turned the heat on. Anyway, all right. So now this will be a good closing topic, is talking about the third type of lateral force resisting system, which is moment frame or moment resisting frame. So here there are a couple different configurations that you could have, right? You could have the option where you've got fixed supports at the base and pinned joints, right? So that's capable of resisting lateral forces and it's stable. Or you could have pinned supports at the base with rigid joints, or these are moment resisting joints, right? They can transfer moment. A third option, I didn't sketch it, but you could also have fixed supports at the base with rigid joints, and that's very indeterminate. We'll look at that condition later on in the semester, but first I'm just going to compare these 2 scenarios. All right, so first we'll look at the pin supports and rigid joint condition. So this is going to introduce the idea of rigid joint behavior. If we have, right, a frame with a rigid joint, we zoom in on that joint, this is what the actual geometry might look like. So, you've got the flange connections to make that rigid. You have the continuity between the flanges through the column, as well as the bolted plate connection there. In our analysis, we would replace that with a stick model, and we would assume that the rigid joint maintains 90-degree angles between the beam and column, right? So when the joint rotates, and it's free to rotate, all the members have to rotate with it by the same amount and in the same direction. So that means in the frame, right, if we apply a lateral load to a frame with rigid joints, if the columns are pinned at the base, then those columns can just lean, right? They're not going to be forced into flexion. They can lean, but the rigid joint is going to force that beam to bend. So it's going to get an S shape like that. Now, if the columns were fixed at the base, then you would also have an S shape in the column. It would look, let's see, so you have to have no rotation at the base, so it would look something like that. It's harder to draw, but we'll look at that later. Now, the other option, right, if you have a pinned joint with fixed base, and then we'll stop after this, the pinned joint behavior is a lot easier to imagine. All right, those members can rotate independently. So as the column leans, right, the beams are just kind of free to rotate however they want. So if there's gravity load on those beams, which there usually is, they'll probably sag under the gravity load, and you'll get an exaggerated deflected shape, something like this. And then in that little frame, right, it would look like this, where the columns have to maintain a 90-degree angle at the base, and under lateral load they would bend, but the beam is just along for the ride. Right, here are a few examples of moment frames. We don't want to do it with wood, or we don't want to attempt to do it with wood because this is what happens, right? Connection failure. So we want to avoid that. And then to close out today, here are a few famous structures that have moment-resisting frames as their structural system. Questions? Comments? Concerns? Okay. All right. I had another thing to say, but I'm going to save it for Wednesday. Hopefully it won't be as hot in here.